Welcome back to our series on microprocessors. In the last videos, we introduced buses and the way a processor communicates with its environment. But now, we step into the very heart of the computer, the microprocessor, often called the CPU or Central Processing Unit. This tiny silicon chip is where all the decisions are made, where numbers are crunched, and where instructions are turned into actions. Today, we'll go deeper into its internal architecture, exploring the Arithmetic Logic Unit, the Control Unit, and especially the different types of registers that give the processor its intelligence and speed.
At the highest level, a microprocessor can be broken down into three core functional blocks: the Arithmetic and Logic Unit, the Control Unit, and a set of registers that act as the CPU's working memory. Supporting these blocks are connections to the outside world: the data bus for transferring actual values, the address bus for identifying memory locations, and the control bus for signals like read, write, or interrupt acknowledge. The Arithmetic and Logic Unit, ALU, is the mathematical brain of the microprocessor. Every addition, subtraction, comparison, and logic operation flows through here. For instance, if the instruction says add A, B, the ALU takes the contents of register A and register B, performs binary addition, and writes the result back into A. If the instruction is AND, the ALU compares each bit of two operands and produces a result according to logic rules. The ALU is connected to the accumulator, a special register we'll cover shortly, and is tightly linked with the status flags, which record the outcome of every operation. In older processors like the Intel 8080 or Motorola 6800, the ALU was simple and worked on 8-bit data. In modern CPUs, ALUs can handle 32-bit, 64-bit, or even 128-bit operations, and many chips contain multiple ALUs working in parallel to boost performance.
Next, we have the registers. Registers are extremely fast storage locations built directly into the processor. Accessing data from a register takes a fraction of the time it would take to fetch it from main memory. Think of registers as the CPU's scratch pad, the place where it keeps the most important numbers right at hand. We'll soon go deeper into each type of register: accumulator, program counter, stack pointer, instruction register, general purpose registers, and of course, the status flags. And now we reach the control unit. The control unit is the conductor of the orchestra. It doesn't do arithmetic itself, but it tells every other part when to act and what to do. For example, when an instruction is fetched from memory, the control unit activates the address bus and asserts the correct control signal for a memory read. When the instruction needs to write back to memory, it activates the write signal. When the ALU finishes an operation, the control unit ensures the result is stored in the right place. The control unit's rhythm is governed by the system clock. Take the Motorola 6800 as an example. It operated with a 1 MHz clock, meaning 1 million cycles per second. Each instruction required between 2 and 12 cycles to complete. So a simple operation like loading a value into a register might take just 2 microseconds, while a more complex multiply or branch could take longer. This clock-driven timing ensures that every part of the processor moves in sync, like dancers following the same beat. We've reached the conclusion of this first step in understanding how the microprocessor works. Today, we explored its architecture and the vital roles of the ALU, registers, and control unit in executing instructions. In the next part, we'll go even deeper, examining how these components interact in real time to bring logic and computation to life. If you found this video helpful, don't forget to like, subscribe, and follow the full playlist to continue your journey into microprocessors and microcontrollers.